Good morning, friends. This is Rakesh Reddy studying in Jamson's Institute of Technology in Electronics and Communication Engineering. Today I am here to discuss about application of numerical methods in electromagnetic analysis for detection by radar. First we discuss about abstract. A novel numerical approach is developed to analyze electromagnetic scattering properties of the moving conducting object based on the finite difference time domain FDTD algorithm. Relativistic boundary conditions are implemented into the FDTD algorithm to calculate the electromagnetic field. On the moving boundary, an improved technique is proposed to solve the scattered field in order to improve the computational efficiency and stability of solutions. Second point, the time harmonic scattered field from a one-dimensional moving conducting surface is first simulated by the proposed approach. Numerical results show that the amplitude and frequency of the scattered field suffers a modulation shift. Then the transition scattered field is calculated and broadband electromagnetic scattering properties of the moving conducting surface are obtained by the fast Fourier transform FFT. Finally, the scattered field from a two-dimensional moving square cylinder is analyzed. The numerical results demonstrate the Doppler effect of the moving conducting object. The stimulated results agree well with analytical results. Introduction. With the development of aerospace technology and deep space exploration, the analysis of electromagnetic scattering properties of moving bodies with high speed has gained more and more attention recently. It has wide applications in the radar detection of high speed movement bodies. The exciting analytical theory of the electromagnetic scattering from moving bodies can be carried out for regular space. Stress obtained the scattering operation in the presence of a moving body. The electromagnetic jump conditions were introduced at a moving boundary by Houston and Adamson. Using the Lorentz transformation, Michelson had developed the electromagnetic waves scattered by uniform moving obstacle. Arnaudov and Venko developed an analytical model to analyze the low frequency scattering process generated by a plane electromagnetic field that is incident upon a moving perfectly conducting. Georgiev studied the inverse electromagnetic scattering problem for moving surfaces. However, it is difficult to analyze general 2 or 3 dimensional bodies since closed form solutions cannot be obtained when the body shape, composition, and transitions are arbitrary. A numerical approach is required to solve the electromagnetic field around a moving body with irregular shapes. We stimulated the scattered field from a rotating two-dimensional cylinder using passing center swing back grids technique based on the FDTV algorithm. Hirani and Kuroda analyzed the electromagnetic field with moving boundaries by combining the Lorentz transformers. They did not, however, discuss how to introduce the incident plane wave source into the FDTV computational domain to deal with the scattered field or moving bodies. Subsequently, a new Lorentz FDTD algorithm is proposed by Jehan et al. They discussed how to introduce the incident plane wave in a moving reference system in the calculations. However, the Lorentz transformation requires at least 2 frames, and a system transformation is needed that increases the calculation complexity, harfons, etc. Calculated electromagnetic scattering from the conducting surface by the FDTD algorithm. However, it cannot be extended to three-dimensional electromagnetic scattering. Since the calculation of the electromagnetic field at the moving interface is based on the reflection model of an infinite conducting plane surface. Based on the FDTV method, we calculated the electromagnetic field on the moving boundary with electric boundary conditions. We analyzed harmonic responses and transition responses of a one-dimensional moving conducting surface. We also analyzed the scattering properties of a two-dimensional moving conducting square cylinder. The proposed numerical approach uses no system transformation and gives the solution directly in the time domain. The Doppler effect of the scattered field from a moving conducting surface was observed in the simulation. Although scattering properties of one or two-dimensional moving objects were discovered in the paper, the proposed numerical approach can be extended to the three-dimensional case. This will be our further research. The present paper is organized as follows. Section 2 introduces the relevant boundary conditions and equations for calculating the electromagnetic field and a moving boundary. Section 3 briefly summarizes the FDTP method and describes the implementation of relativistic boundary conditions. Section 4 presents the analytical formula of a moving conducting surfaces. Section 5 discusses the simulated results of a one-dimensional moving conducting surface and a two-dimensional moving conducting square cylinder. 2. Relativity boundary conditions for a moving conducting object. For a stationary boundary, separating regions 1 and 2 and tangential components of and the normal components of are continuous across the boundary. One the moving boundaries between region 1 and region 2, however, the components of electric field and magnetic field should satisfy relativistic boundary conditions. The derivation of these conditions in its general form is well presented in 14 and yields. Below, the equations are related to the topic. Where substitute 1 and 2 donate fields in regions 1 and 2 and are the electric field, electric flux density, magnetic field and magnetic flux density respectively, and denote the surface charge and current density is the velocity of and magnetic flux density respectively, and denote the surface charges and current density is the velocity of moving interference assumed to be uniform. We define the surface normal point from region 2 to region 1 when R1A 1D reduced to equations of boundary conditions of stationary boundaries. When we consider region 2 as a perfectly conducting medium, relativistic boundary conditions become a one-dimensional moving conducting surface insulated by a plane wave is shown in figure 1. The incident electric field is polarized in the x direction and incident magnetic field is polarized in the y direction. The conducting surface is parallel to the XY plane and moves along the plus z axis with the speed of v. Where subscripts 1 and 2 donate fields in region 1 and 2 under the electric field electric flux density donate and one-dimensional moving conditions. It is a diagram for 1D infinite surface and incident wave. According to the relativistic boundary conditions, total field including incident field and scattering field components of E bar and H bar on the one-dimensional moving interference are given by Ex equal to V dot mu dot Hy. The relativistic boundary conditions can be easily implemented for the 2 and 3 dimensional. It is important to note from 2A to B to C and to D that the scatter motion perpendicular to the surface normally reacts in boundary conditions similar to those of fixed object. The reason is that the term n cap dot V bar is now equal to 0. Third, a numerical method model for a moving conducting object. The finite difference time domain FDT algorithm was introduced by E to numerically solve Maxwell's two equations using finite differences in a one-dimensional case. Maxwell's two equations are equivalent to the following scalar equations. Dou xy by dou z equal to E dou ex dou t plus sigma ex. Dou ex by dou z equal to minus mu dou hy by dou t minus sigma m hy, where sigma m denotes conductivity and magnetic intensity respectively. A finite difference time domain algorithm was introduced by E to numerically solve using finite difference in one-dimensional case equation to follow scalar equations. These are the formulas and equations for the finite difference equations 5, 6a, 6b and 7. In the study of electromagnetic scattering from the moving conducting surface. The electricity boundary conditions are implemented in the FDTD method. The FDTD scattering model for the moving conducting surface is shown in figure 2. Radiational boundary conditions are implemented to truncate the FDTD computational domain. The FDTD computational domain is separated into two parts. One part is the total field region including the moving conducting surface. The other part is the remaining region called the scattered field region. The incident plane was wave is introduced to the total field region by the connecting boundary. In order to study the scattering field from the moving conducting surface, the observation point is placed in the scattered field region shown in the figure 2. This is the figure, the radiation boundary, the connecting boundary are represented by arrows, and the down scattered field region and total field region is there. The relativity boundary connection is only implemented for the electron field at the moving condition surface. According to it should be enough to model the scattering form. A moving object here should be implemented for the electric field on the moving boundary at each time step. When the surface moves, however, the moving boundary cannot be just at the position of a component in the FDTD model. At the time of T1, the connecting surface is at the position M as shown in figure 2. The distance between the electric field component is closest to the moving boundary, and the moving boundary is more than lambda z by 2. Subsequently, the conducting surface moves at the position n when t is t2. The distance between the electric field component is closest to the moving boundary, and the moving boundary is less than delta z by 2. Therefore, is implemented only for the Ax component closest to the moving boundary. The closest distance between the Ax component and the moving boundary ranges from 0 to 1 spatial increment. The accumulated errors may be FDTD equations non-convergent after many time step calculations. The resolve this problem and improved technique is proposed in the paper from figure 3a and 3d, and arrow represents the electric component X and the dot represents the magnetic component Hy. The moving conducting surface is assumed to be relatively static in the FDTD domain as shown in figure 3a and 3b. Thus, the position of the X component becomes fixed at the moving boundary all the time. By introducing proper incident fixed field values to the FDTD total field region and moving the observation point, the scattered field from the moving conducting surface can be stimulated. The stability of solutions is satisfactory. Electromagnetic field components at the truncate boundaries are calculated by the radiation boundary conditions, and the rest of electromagnetic field components in the FDTD domain can be calculated by 5 and 7. This is the diagram we talked before, that the radiation boundary and connecting boundary multi-surface. Analytical formula for the scattered field for a moving conducting surface. When an incident sinusoidal plane wave of angular frequency omega and unit amplitude is normally incident on a moving infinite conducting surface with speed v, the scattered electric field is given by 16. E is equal to minus E dot 1 minus V by C by 1 plus V by C into exponential j into 1 minus V by C by 1 plus V by C W omega t minus kz plus 2 jk or naught minus v t naught by 1 minus V by C. When g naught equal to v into t naught minus t minus t naught plus r naught is the position of the surface boundary with respect to the reference point, and r naught and t naught are initial values. It has been seen from 9 that the Doppler effect 17 is apparent in the scattered field, but both frequency and amplitude of the scattered field are changed by multiplying the same factor, which is defined as alpha equal to 1 minus V by C by 1 plus V by C. This is the formula, this is the graphs about the numerical results. Conclusion: electromagnetic scattering from a moving perfectly conducting object in the steady state one frequency and transition state broadband has been analyzed by the proposed numerical method based on the FDTD algorithm. Relativistic boundary conditions are incorporated to solve the electromagnetic field on the moving boundary, and an efficient technique is introduced to calculate the electromagnetic field around the moving conducting object. The numerical results illustrate that the range of the frequency and amplitude shift of the scattered field varies with the moving speed of the object. By comparing stimulated results with theoretical results, the accuracy and validity of the numerical approach are evaluated. Contrary to other numerical methods using the Lorentz transformation, the proposed numerical approach uses no system transformation and gives the time domain solution directly. It is convenient to analyze broadband scattering properties of moving bodies. This approach can be applied to many practical engineering problems, such as detecting the speed and direction of moving satellites or aircrafts by radar images. Thank you.